Morning. My name is Mike Urynowicz. I'd like to welcome everyone to the 13th International Congress on Subsurface Environment. And my presentation today is going to be on managing groundwater for biomass with carbon dioxide removal plus RNG. So this is referred to as Bikers plus RNG. It's a new methodology that we recently developed and are currently commercializing in Wyoming's Powder River Basin. So the bulk of this presentation is going to be on the technology, and then the last couple slides, I'll talk about some of the approaches we're taking with respect to groundwater monitoring. So just a brief introduction here. Again, my name is Mike Urynowicz. I'm the director for the Center for Biogenic Natural Gas Research at the University of Wyoming. Uh, I have been on a 2-year leave of absence from the university, working with Cowboy Clean Fuels. Actually, just a few weeks ago, I'm kind of transitioning now back to the university, but a few weeks ago, the semester started and classes began. But still serving as the Chief Technology Officer at Cowboy Clean Fuels, as well as kind of getting back into academics. So the Center for Biogenic Natural Gas Research is where we developed these technologies that Cowboy Clean Fuels is currently commercializing. Okay, so what is it that Cowboy's working on? Is this biomass plus carbon dioxide removal with renewable natural gas? It's again, it's probably a technology that most of you aren't familiar with. Maybe some are familiar with Bikers technologies in general. The technology designed to remove carbon dioxide from the atmosphere and sequester it deep underground, as well as produce RNG in the process. So it's a scalable technology. Again, it produces carbon negative RNG, and we get permanent sequestration of carbon dioxide in the coal seam. And this is all done through microbial processes. What's one of the novel aspects of this technology is that we're leveraging natural processes. So a way to envision kind of what's going on. These coal seams are over 1,000 feet deep, and the natural gas that has been produced in these coal seams, the coal bed methane, is actually what's referred to as secondary biogenic in nature, meaning that it was produced in the coal long after the coalification process, long after the coal was produced because of temperature and pressure. Microorganisms re-inhabited the coal and produced this natural gas through natural processes, biogenic processes. So what we're basically doing is we're leveraging these natural processes. We're also taking advantage of the coal's ability to adsorb carbon dioxide. It actually adsorbs methane as well, but it adsorbs carbon dioxide 4 to 5 times greater than it does methane. And we're also utilizing existing natural gas assets. So if you're familiar with the Powder River Basin, over the last 30 years or so, there's been a significant coal bed methane play where a significant amount of CBM has been generated over the years. So there's existing infrastructure, existing wells, existing pipelines to recover that methane and put it into the market. So over the years, that production has waned. And what we're doing basically is employing this technology to transition from coal bed methane, a fossil fuel, to carbon negative renewable natural gas. And again, doing this by leveraging the natural processes, by delivering an alternative feedstock to the microorganisms. So instead of degrading coal, now they're degrading molasses, which is a extract or byproduct of the sugar beet to sugar manufacturing process. So the methodology for this technology was just developed, recently developed by eco-engineers, and it's basically a framework for quantifying, monitoring, and verifying carbon dioxide removal and geologic sequestration, as well as renewable natural gas production. So, in this methodology, um, all the carbon's tracked and monitored, and it includes. It was basically developed to comply with ISO 14,000 standards and has went through extensive peer review. And we just completed this earlier this year. So again, this is a new technology, a new methodology, and it's newly being commercialized in the Powder River Basin. So let's talk about the technology a little bit. Excuse me. This is a technology that we patented again at the Center for Biogenic Natural Gas Research. It's a biomass with carbon removal and storage, biker's technology, but where we combine that with the ability to produce renewable natural gas in these economically depleted coal seams. So to follow this process, the first thing that really happens is sugar beets are grown. So carbon that is in the atmosphere in the form of carbon dioxide is taken up by the sugar beets, and at the end of the growing season, it's processed at sugar beet refineries into sugar, sucrose. A byproduct of that is sugar beet molasses. So that's what we start with. That's the number one here. That's the biomass injection. So basically what we're doing is we're decoupling these microbial processes that occur in these coal seams and supplying an alternative feedstock in the form of sugar beet molasses. So again, think of it from a carbon balance standpoint, think of that carbon existing in the atmosphere being fixed in the form of sugar beets, and then us taking that byproduct of the sugar beet to sugar production and using it as the feedstock that we inject into the subsurface. So in the subsurface, the microorganisms use that feedstock and produce carbon dioxide and methane. So the most important part of this process is methanogenesis. So the CO2 and the methane are being formed in situ, again, 1,000 feet down within these biogenically active coal seams. We use the existing infrastructure to produce the renewable natural gas. The coal has a greater affinity to absorb the carbon dioxide. So the carbon dioxide, that fraction of the carbon, is preferentially adsorbed onto the coal. And the gas that we produce through that existing CBM infrastructure is 97+% methane typically, with a very small, 2 or 3% fraction of carbon dioxide. So you can imagine these coal seams as basically a scrubber that allow the carbon dioxide to be sequestered in this process. So a little bit different schematic here, just tracking the carbon. Again, the CO2 is atmospheric CO2. We grow sugar beets, or the farmers grow sugar beets. It goes to a sugar beet refinery where it's processed to sucrose. The byproduct of that is molasses. That's what we're using as our feedstock, but the microorganisms are very robust. They can use other feedstocks as well, but that's the one we're currently using. We inject that into these coal seams. Again, think geobioreactor where the microbial processes occur. And in situ, within those coal seams, deep underground, methane and CO2 are produced. The coal has a natural affinity to preferentially adsorb the CO2 over the methane. And as a result, we're able to selectively produce the methane as renewable natural gas and use the existing infrastructure, the existing natural gas infrastructure, to deliver that carbon negative RNG to market. So the feedstock, with any type of bikers type technology, having locally grown feedstock is very important. Transportation cost can add a lot to this process, which is mostly, there's not a lot of capex here. It's mostly feedstock is where most of the cost is incurred. So again, we use molasses. You can see here in this map, You can see a sugar beet. You can see where sugar beets are grown, and you can see where the triangle unit is in just outside of Gillette, Wyoming, in the Powder River Basin. So we're able to access sugar beet molasses and also molasses desugarized solubles as our feedstock from Wyoming, the Wyoming uh, facility, as well as other sugar beet growing areas and processing facilities located in neighboring states. So let's talk a little bit about Wyoming's Powder River Basin. It's I think the first or second largest coal basin in the world. It's again, I mentioned that the coal bed methane. You can see Wyoming CBM production here in the middle figure, how things peaked in the mid to late 2000s there, 2010, but have been, as far as production, CBM production, but have dropped off significantly ever since. So in the Powder River Basin, there were over 20,000 wells that were drilled, pipelines that were put in, roughly about 10 or 11 billion dollars of infrastructure to recover the coal bed methane. And how that was done traditionally uh, is that water would be produced, and as the water would be produced, the hydrostatic head would be reduced, and creating a different equilibrium condition within the coal seam, allowing the methane to desorb. There's also CO2 adsorbed onto these coal seams, but it actually takes a vacuum typically to remove the CO2. It's locked, again, much more tightly onto the coal than the methane. But so, in essence, what we're doing is we're stimulating that microbial activity to produce uh, natural gas real time. We're decoupling the coal as the feedstock and introducing an alternative feedstock, the molasses, and we're using that existing infrastructure to produce renewable natural gas and sequester carbon. You can see that bottom slide here. That is the difference in adsorptive capacity of CO2 versus methane. So you can see the coal has a much greater affinity to adsorb the CO2 than it does the methane. A little bit about the triangle unit. We started Cowboy in 2020 and acquired, I think, in 2022, about 139 wells, um, which we refer to as the triangle unit, just outside of Gillette, a little over 12,000 acres. And in 2024, we commenced operations. So in a little over a year now, we've been injecting molasses, and our RNG production is starting to come up. We've been sequestering carbon dioxide, and we're looking at now to kind of scale up the operations. Just a little bit about the markets. So Cowboy Clean Fuels has two markets that it delivers into: the renewable natural gas market and the carbon dioxide removal market. So attributed with renewable natural gas are environmental attributes. We're able to sell our gas at about $20 per MMBTU in the United States. Prices are actually higher in Canada, but this is because of the environmental attributes. The fact that the carbon, the RNG is actually carbon neutral. And again, think of the carbon balance, CO2 coming out of the atmosphere, and half of that CO2 being sequestered into the coal, at least half, and then the remaining amount being produced as RNG. That allows us to produce zero or carbon negative gas. So that's one market. The other market is carbon dioxide removal. So as part of this process, we're also sequestering carbon deep underground in these coal seams. And this is an emerging market. The RNG market is actually a voluntary market, but the carbon dioxide removal market is also voluntary. And there's a lot of companies that are trying to offset their carbon emissions by purchasing carbon dioxide removal credits. So we're basically able to offer both. The carbon that we inject, the total organic carbon into the coal seam, can either be monetized as RNG or sequestered and monetized as carbon dioxide removal credits. Okay, so a little bit of that was a lot about the technology, but again, probably a new technology for most of you. A little bit about monitoring. So, what really makes this technology possible is the ability to differentiate the renewable natural gas from the fossil-based gas, which is the carbon, the coal bed methane. So the coal bed methane, think of that as dead gas. That's gas that's been generated a long time ago, and it doesn't have a carbon 14 signature. So we use radiocarbon isotopic analysis to determine the percent modern carbon. Basically, we send our gas samples at the point of sales to have them analyzed for percent modern carbon through radiocarbon dating. And that allows us to determine what fraction of the gas that we're producing is the new carbon and what fraction is the old carbon, the coal bed methane. So what is the carbon negative or carbon neutral RNG and what fraction is the CBM. So this is the technology that really allows us to implement this and differentiate between those two forms of renewable natural gas. We also use stable isotope analysis. So you can see this figure here. Stable isotope with respect to carbon is carbon 13 and carbon 12. But in particular, we look at carbon 13 analysis, and we can relate that to carbon 14% modern carbon. So the shift in carbon 13 is directly related to the percent modern carbon. We've been working on developing these methods for many years. So that's the gas. Groundwater, of course, is also very important. We do basically the way this is implemented is we have a single injection well and kind of like a 5-spot where we have adjacent recovery wells, and we monitor groundwater and we produce gas in those adjacent recovery wells. So the groundwater, we measure typical groundwater quality parameters, total dissolved solids, pH, etc. And we also apply isotopic analysis to the groundwater as well. And this is a patent that was recently issued entitled Methods for Microbial Gas Production and Use as Isotopic Tracer. So we're able to use the gas in the trapped or free gas phase as a tracer. We're also able to use the dissolved gas in the groundwater as a tracer. And we're also able to look at, use both of these in the context of fate and transport through the coal seam. So we're currently monitoring the gas production and groundwater to create a conceptual model with respect to the fate and transport of that carbon in the form of molasses and ultimately all the breakdown products, including the gas, the methane, the CO2 in our system. So another isotope of interest is deuterium. Deuterium is another stable isotope that we're able to correlate with percent modern carbon with radiocarbon dating, and tritium, which has a lower half-life. We're just starting to look at tritium analysis as well to differentiate between new and old carbon at the site. So a lot of really interesting groundwater monitoring techniques that we're utilizing. We're using the gas both in the free and dissolved form as a tracer at the site, using both stable and unstable isotopic analysis to understand how that gas is moving through the formation. Okay, with that, I'd like to conclude my presentation and thank you for the opportunity and look forward to the discussion and any questions that you might have. Thank you.